Dr. Jacob Torres, how important is potassium?
Man, very important, I'll say. It depends on what you're asking for, though.
Well, if we're looking at the whole world of minerals in general, people focus on like sodium as being the most important. And we've almost had this, how do I put it? I don't want to say demonization of potassium, but this overshadowing of potassium by sodium. Mm-hmm. And then you go to the store and you can only buy potassium in like 99 milligram tablets. So you must think it's either dangerous or you don't need that much of it. But I mean, most of your research at UCSB, all of your research at UCSB is in the world of kidney health. Mm-hmm. And obviously potassium is critical for kidneys. But I mean, how does potassium work just generally in the body? Specifically in the kidneys though. And then what is the level of importance of potassium versus say sodium, magnesium?
After today's video, I put a link down below for LMNT electrolytes. They are not sweetened with erythritol. LMNT electrolytes are 1,000 milligrams sodium, 200 milligrams potassium, and 60 milligrams magnesium. But that link down below gets you a free sample variety pack with any purchase of LMNT electrolytes. So whether you purchase their sparkling, whether you purchase their stick packs, or whatever, you get a free sample variety pack, and that's exclusively using my link down below. That is drinklmnt.com/Thomas. Again, drinklmnt.com/Thomas. Really interesting stuff. They curb my appetite entirely, but I also have them in a fasted state, and I sip on them during my fasted workouts because I feel like I actually get replenished, but I also get my cravings satisfied. So that link is down below in the description.
Okay, all right, there's a lot of stuff in there. So, we have these requirements for these particular, we call them cations because they're positively charged ions. And sodium and potassium are kind of like the central players. And calcium, I would say, is also probably a central player. The main reason being is that every cell is required to do work, right? They all want to do work in some way. And the way they do this is they create an energy potential. And the potential is generated from the difference between extracellular potassium or sodium and intracellular potassium or sodium. So it'll pump ions across the membrane in order to create this gradient. And then now once it builds up enough on one side or the other, it can then use that to perform work. So, the higher concentrations flow down to low concentration. So if you want to couple the movement of another molecule, you would couple it to the movement of potassium or sodium. And then you would just move it up and down the gradient depending on how you've generated that gradient.
So if you look at, why is it that it almost sounds as though sodium and potassium need to be in equal amounts, but do we just lose more sodium? Is that why sodium seems to be more, it seems as though we need more sodium than we need more than potassium, or do we really need more equal amounts?
You actually need far more potassium. Potassium is far more important in molar concentration. Like you need a lot more potassium. Yeah. So in every single cell every neuron requires sodium and potassium because that's what generates what they call the action potential. That's the neuronal firing, the electrochemical signal that comes from a neuron is caused by a depolarization event. And that event causes the movement of sodium into the cell and then potassium out. And then you have this movement that kind of propagates along the axon, which is the long portion of the neuron that goes to its target. And so that requires a lot of potassium and sodium movement. And then in the kidney, you have a similar pump, this sodium potassium pump that's always pumping back and forth. And potassium seems to be, always you're peeing it out all the time because it's pumping things in. So the coupling of potassium to sodium's getting pumped in and potassium's getting pumped out, for instance, that causes you to pee out some amount of potassium. This is a really complicated part of it though, because there's many different mechanisms of like how sodium and potassium are regulated in the kidney. But it turns out that you actually decrease the amount of sodium you have by increasing your potassium intake. You just pee out more sodium as well. So a lot of the concerns over like blood pressure with sodium are related to like if you eat too much sodium, then your blood pressure goes up because the blood is trying to always maintain the same concentration of sodium. So you have to change the volume. So the volume is going up or down depending on the amount of sodium that's in there. So that's what affects the blood pressure, because if you have more sodium, then you have to pull that into the blood. the volume of blood has to increase in order to keep the concentration the same. Does that make sense?
Yes.
Yeah. So then that causes blood pressure to go up because now you have just more volume pushing on things. And so that process is like the part of why sodium is involved in blood pressure. So we focus really strongly on sodium for that reason. But it turns out that when you increase potassium, you have a tendency to pee out more sodium. So it actually brings the amount of sodium down in the blood. So it actually has a positive effect on blood pressure because you're just peeing out this excess sodium. And there's a lot of reasons why that happens in the kidney. But that means that your requirement for potassium goes up because they're both getting peed out. So then you end up it just ends up being that the ratio is more important, that you need like a far more potassium during the day.
Do you typically deplete sodium and potassium like during exercise at about the same rates?
Yeah, I think that would be accurate. Yes. I think that I'm trying to think if it would be different. I don't think any reason why you would use any more than one or the other, because they're kind of doing their thing. And then as they go through, as you increase filtration, so filtration in the kidney goes up, then you would pee more out. So I think that would be the only thing, the only real effect. I would imagine during workouts, that's a good question, is if your potassium excretion would go up. I don't know. It's a good question.
Yeah, I mean, it's just when you look at it, part of me wonders if so much of the ratios of sodium to potassium that we look at and we think about are governed so much by what is in supplements and it's almost as though like when you see we can only have 99 milligrams of potassium. Mm-hmm. And then the electrolyte companies are like, well, we got to be careful. We don't want to put too much potassium in. Has this possibly dictated how we look at potassium?
I think so.
It's in an effort to protect people from potential adverse heart effects with high levels of potassium, which you need really high levels of potassium to have that happen. We've kind of framed people's brains differently to where we're so sodium focused, we almost forget about potassium.
Yeah, I think that's true. I think that they sell them in these 99 milligram capsules. I think there's just like a rule about that, just because if you have too much potassium, you can stop your heart. If you have chronic kidney disease where you can become hyperkalemic, and that cause some issues with the heart as well. So they kind of make things for that reason. Like they don't want people to overtake potassium for that. But you need multi-grams of potassium per day. So you're very low below that level. And when like I mentioned with the blood pressure issue, that's where the focus on sodium it's been so much on sodium and not on potassium realistically. Like it should be kind of understood that they work together to control these different processes. And yeah, we just kind of really focus on the one over the other for that reason.
Is there some evidence? So let's say someone goes out and has a bunch of sodium and has a bunch of water retention as a result of it. Does taking potassium counteract that and actually have somewhat of a diuretic effect and bring that down?
Yeah. And so, potassium intake causes natriuresis. So natriuresis is just peeing out sodium. So that does happen. Yeah.
So you're not necessarily peeing out potassium at the same rate. So if you increase your potassium and you start increasing sodium excretion, are you just by the nature of urinating also losing a sufficient amount of potassium too?
Yeah, you're losing a lot of potassium at the same time. But I think there's another mechanism to pull a lot of the potassium back in. So I've got to check the ratio, but it is a lot that both of them get peed out.
How much of a role do the kidneys play just in overall hydration?
Oh, just the regulation of hydration. I mean, they are
aldosterone and all of that whole.
They are the regulator of water. So if you do not have proper aldosterone and vasopressin signaling, then you cannot maintain water. Like your water balance does not work. So that's just that is like the main function of the kidney is to control, amongst many things, is the total water content of the body and the ion concentration of the blood.
So when someone starts to say become dehydrated, there's kind of the old, I don't know, people talk about it. I don't know if it's actually true. Like when you're dehydrated, mm-hmm. Does it put more stress on the kidneys, or is that really not a thing? Like is hydration actually good for the kidneys, or is it really just like you're giving the kidney something to do?
I think the stress comes from, the concentrating effect of the kidneys has to increase. So your kidneys make either dilute or concentrated urine, depending on the circumstance. If there is a lot of extra water, then you make more dilute urine, and it just the amount of stuff might stay imagine that the rate of stuff going through might be very similar, but just the concentration is changing because the dilution factor, right? Like you're either having more or less water in there. So if you get very concentrated where water content is now very low, then you can start to build up other products, like because now the pH might change. So the pH will drop because the concentration of these compounds is going up, and that causes a drop. So like ammonia might start to become a thing. And then you have to you have to make there's like buffering things that have to occur to deal with like ammonia production or other solutes that are in the filtrate.
Got it. So it's like almost as though, I mean, just because they have to do with hydration, it's almost as like they're not necessarily the first thing that's impacted with dehydration.
Mm-hmm.
Okay. So because it's, talk to people that have concerns with their kidneys there. It's almost as though, okay, well, I have to keep adequately hydrated to protect my kidneys. And my thought has always been like, yes, the kidneys are involved there, but it seems like there's a lot of other things that probably take the hit first in dehydration, not just because kidneys are involved in hydration.
Yeah, they're definitely affected. I would say that adequate hydration is important for that reason I was stating, just to make sure that you don't have overly concentrated urine, because that's the potential for injury, is just that it's creating this over concentration in the nephron. It's like the tubule part where it's doing the filtering, and that could cause like kidney stones, like if you just have really concentrated solutes in there. So that's where the concern would come from.
Are there different types of potassium that people can get, whether it's through food or supplementation? Are there different forms, or is potassium just potassium? I mean, like with magnesium, for example, in supplemental form, you've got magglycinate, you've got threonate, you've got, whatever, dimagnesium malate, all this stuff. Like potassium, do you know anything about that? Is there anything there that matters, or is it just like, just get your potassium?
That's a good question. I know that there are affinities for potassium that are different between different compounds. And in plants, I think usually it's like in carbonates and stuff, like there's these other, these lot of different carboxylates that bind to the potassium that is what you're absorbing. Yeah, I don't know. I always heard that glycinate was a good version of it. But in research, they just use potassium chloride, the most like basic version of potassium supplementation, and it seems sufficient to be absorbed. I have no idea like what would be the difference between them. Sometimes it feels like there probably is no difference. Yeah. And like potassium citrate is a really, well researched and used version of potassium that gets supplemented frequently. Yeah. Yeah.
If you look at, I've always talked about from the side of muscle cramping, it's like we've talked about magnesium muscle cramps usually are occurring long after exercise, whereas potassium cramps are kind of the ones that occur during exercise. Like there used to be, I know I was involved in a clinical trial with magnesium, and that's kind of what we're looking at with even with restless leg syndrome and leg cramps. And it was like, okay, it's like mag deficiency there was like the cramps that happen in your bed and your calf, post-exercise, not even necessarily post-exercise, just in life.
At night,
yeah, it's a much more of a magnesium thing, whereas potassium, if you're going to cramp, that's usually what the issue is when working out. Is that something that's regulated? Like, is there an interplay with the kidneys and the muscle cramps, or is that happening like solely at a musculoskeletal level that's operating independent of the kidneys?
Yeah, I think that's just an overall, if the kidney is not pulling in potassium sufficiently, then that's probably the issue. Because you're describing that the cells aren't able to reconstitute the polarization. That's what the rectifying potassium channel is needed for. So it just kind of like cramps and stays activated. And the kidney itself, of course, is going to regulate the amount of potassium in the blood. But at that point, it's probably there's just not enough potassium in general that's getting reabsorbed. So it's just probably the intake is too low.
I know, again, you're not a dietitian. This isn't necessarily what you can make a recommendation on, but I mean, are we as a population generally pretty deficient in potassium, and are we not getting enough?
Yeah, for sure.
Yet we're getting probably an abundance of sodium, I would imagine. So we're probably, and does that ratio actually get worse? For example, the more sodium you take in addition to like sort of the effect of, the diuretic effect, do you need more potassium to match that? Like as the ratio changes, does your demand increase. So if you're eating a high sodium diet, just by standard American diet standards, you're just eating that, do your potassium requirements increase to match the sodium? Or is it better to say, hey, bring your sodium levels down to sort of match it that way?
Bringing the sodium levels down is I think the correct thing here. The reason being is that the research on both potassium and sodium both have U relationships.
Okay.
So the high and the low are both not good. So if you have too much potassium, that's been shown to be bad. Too much sodium, bad. And they both have this like U distribution of like that middle spot is where all of the benefits at. So yeah, we definitely need a greater potassium to sodium ratio. So I think that, 3-to-1, 4-to-1, is probably a good is better. I think there's some literature out there that's saying that ancestral potassium ratios could have been high as 10-to-1. So we could have been just getting lots of potassium, because sodium is very difficult to find out in nature. That's why animals find salt licks, because it's just such a hard thing to get a hold of. And they see these interesting stories where like animals will migrate to like some hole in the ground that they find, and they eat the dirt because there's sodium in it. It's like such a requirement, but it's so rare. And now we have preserved foods, and preserved foods are full of benzoate, sodium coupled salts, and those are like where people are getting most of their sodium now. And also, interestingly, the chloride is a very important part of the story too, because chloride ratios are also important for balancing things out. Like we don't have a benzoate transporter, but we have a chloride transporter that's very important. So it detects that ratio as well. So like when we do get salts, a lot of times we're getting them in potassium or sodium chloride. And so that's also very relevant.
So if it's in sodium benzoate versus sodium chloride, the body can basically, that can metabolize the chloride? It can't metabolize the benzoate? Is that what it is?
Well, there's a different transporter. So there is a chloride transporter that is just similar to the like I mentioned with the sodium and potassium channel that builds up gradients. Chloride has a pump that's similar and couples chloride to like the movement of ions as well.
Got it.
So chloride is an essential nutrient as well.
So generally when you're looking at table salt and you're looking at like sodium chloride, are those usually coupled in a ratio that is obviously safe for human consumption, but is there a disadvantage to consuming potassium chloride or sodium chloride if you're using that in, let's just say, supplemental form to try to increase one or the other? Or is it usually just enough chloride? Do they know what they're doing with that? Or is it just...
Oh yeah, I don't know if anybody's thinking about that part of it, but I think that the ratio is of chloride and of chloride to potassium and sodium is important. I think that we just get enough chloride most of the time, so it kind of doesn't matter. But I could see a scenario where you could be deficient in chloride salts in some way. But it's not like a really big research area that I'm familiar with. But I do know many transporters that require chloride for their function. So if you're getting sodium and without the chloride in appreciable amounts, at some point it will become it could become a problem. Yeah,
that makes sense. I mean, it's interesting. Growing up, I had a lot of horses, and we had 10 acres or so, and we would you could put a salt lick anywhere in that pasture, and the horses would find it, right? And it was always, I remember being a kid and just being confused and asking my mom, and she's like, well, salt's really important because it's so basic. She's like, well, look at what they're eating. They're eating hay. So like, do you think they're really getting salt? So like, you could practically bury that thing and they would find it. And I've referenced that in videos. I've talked about how, I don't know if you're familiar with this. This is interesting. It's totally out of your area of research, but there's a thing called in the hindbrain called NST neurons.
Okay.
And when you consume salt, there's actually a gustatory response that sort of solves cravings a little bit just because of that, because we have such a desire for salt that we will find that. And a lot of times when we're craving things, we're actually craving salt in that sort of evolutionary perspective. I don't think many people are actually like so deficient in salt where they're craving salt. I mean, there are probably a million other reasons why they're developing cravings, but in a starvation sense. And I came upon this research when we were talking about fasting a lot, because if people are doing a 3-day fast or whatever, they're not, then there's a good chance that, some minerals are depleted and you start getting these cravings for sugar. It's like, hey, consume a little bit of table salt and watch what happens to your cravings. It's pretty wild because of these neurons in your hindbrain. Very mechanistic stuff, but it also makes some sense, that from an evolutionary perspective, we're like seeking this out. But I'm coming back to this because meat has a fair bit of potassium in it.
It does,
you know,
yes.
And it's like you come back to how we used to eat, right? It's almost like, okay, like there wasn't a bunch of sodium in that meat. There probably was a good amount of potassium. So getting to that 3-to-1 or whatever was probably a lot more easily achieved in sort of an ancestral type diet.
Exactly.
Yeah. What do you think about, or actually, can you explain in layman's terms how insulin impacts mineralization and in that entire aspect? Because I know from my research in the ketogenic world that when insulin levels are low, you lose more minerals. Is that simply just a urination thing? What's going on there?
That one, I'm not versed in this mechanistically, so I don't have a good answer for you. I do know that that's a phenomena that occurs, but I do not know the exact mechanism for that.
Yeah,
I'll let you down on this one.
Yeah, no, it's well, I don't know.
I'll go look it up.
All that I have been able to find, so to like, as far as this is concerned, is when insulin levels are low, is you excrete more, and some of it probably has to do with glycogen. What was it, like 3.7 grams of water for every 1 gram of carb or something like that, which still actually raises an interesting question for me that we may or may not know. I know that if I consume 300 grams of carbs, I don't gain that much in water weight. It's also, I don't know what the deal is with the 3.7 grams of water per 1 gram of carbohydrate, but if I consume, 300 grams of carbs, I'm not storing 1,200 additional grams in weight. It never seems to be that way. So there's something off in that math too.
Well, part of it's not all of it's going to make it into storage. That's the main thing.
Yeah, that, and you also don't know how glycogen depleted you are to begin with.
Right.
I don't think via gluconeogenesis and whatnot, I don't think many of us are sitting in a completely depleted state. Maybe you're at 50% or so.
That's pretty hard to do.
Yeah. So if someone were to potentially start supplementing with potassium, is there a way to sort of titrate up to find like what optimal is? I mean, is there a way someone should be feeling?
I mean, the easiest thing would be to just track your intake. I mean, that's how I would do it. I mean, I would just figure out like where am I at? Where do I need to be at? Am I exercising more? That would, obviously increase the necessity for sodium and potassium, but I would really just track it and then figure out like, am I deficient in just general?
Yeah. So you just creep it all the way up until your heart slows down. And
Back off.
Don't do that. No, I think that's really, one last question with this. What role does magnesium play within the kidneys with all of this? Is magnesium playing a very critical sort of relaxation role, or?
Well, magnesium it has a transporter. So it's magnesium's crazy. Okay, so there's just a lot of stuff in the kidney that there's just so many differences between the segments. Like, so, the kidney is like this long tubule, and every one of those segments has different transporters for every single mineral. And magnesium is another one of these minerals that has, as it goes through the nephron, there's different segments that are pulling in magnesium for different purposes. Some of it gets pulled in just paracellularly, like in between the cells, and some of it is actually getting pulled in by active transport, and it's pulling in with different compounds. So there's different things that it's functionally bringing with it, and it also is regulated by the amount of potassium and calcium and sodium that's going through the nephron as well. So it's really just playing with all of these things. It's the interplay between the concentrations that kind of dictates like what's coming out in the urine, because it's just so sensitive to those minor differences. But it does have, magnesium has a bunch of roles in like the proteins that hold tissues together. Like it has a role in keeping like the junctions together and stuff. So it has other functions besides just like, relaxation. Specifically, you're thinking from the neuron side of it. Like, like binding to the receptors that are activating, muscular contraction. So that's like the acetylcholine receptor. So that story is like, that's its own thing. In the kidney, it's just more of like a co-transporter, a cofactor for bringing things in or out. Yeah.
I guess what I'm learning from all this is that the kidneys are a lot more important than I thought. So someone that only has one kidney, is the strain on that kidney significantly higher?
Yeah. So the interesting thing about kidneys is if you decrease kidney function in one, the other kidney will actually grow somewhat they call it compensatory hypertrophy. So if you take a kidney out, the other kidney gets a little bigger and just like does some more work. But it does put more strain on it, but it whatever that mechanism is of growth, it seems to be some sort of functional thing as well.
Yes, man. Well, Dr. Torres, where can everyone find you, man?
drjacobtorres.com, easy place.
Cool. And then I'll link out to some of the other stuff. You've got a product, Keto Citra, as well, which I'll link out to down below.
All right.
And thanks, my man.
Yeah, thanks.